Hi, I'm George Woodbury from College of the Sequoias in Visalia, California, and in this video we're going to talk about the intermediate value theorem, which states if a function f is a polynomial function with real coefficients, and we know that for values a and b, that f of a and f of b have opposite signs, meaning one is positive and one is negative, then we know there's at least one real zero between those two. So what we know about polynomial functions with real coefficients is that they're continuous. And say we have a graph where for a, f of a is positive above the x-axis, and for b, it's negative below the x-axis. Since the function is continuous, when we draw the curve from f of a to f of b, let me just mark what those are, it's impossible to draw it without crossing at least once. And this would be true if f of a were negative and f of b were positive. So this lets us know that there's one zero, at least one zero somewhere in here. Then we can go about some different techniques to find it. But this shows that a zero exists. Now, one thing to warn you about is, let's say that f of a and f of b have the same sign. So in this case, let's say they were both positive. That doesn't mean that there's not a zero between them. It's just that there's no guarantee that there's a zero between them. For instance, if I draw a parabolic shape, now I can see that there were a couple of solutions there. So the intermediate value theorem is to show that a solution, a zero, must exist. It's not to eliminate zeros from any interval. All right, let's use synthetic division to show that this function, f of x equals x cubed minus 2x squared plus 4x minus 9, has at least one real zero between these two numbers, 2 and 3. So what we're looking for is we'd like f of 2 and f of 3 to have opposite signs, one positive and one negative. Let's see if that happens. We'll use synthetic division as the directions state. You could just evaluate the function as well. We'll start with 2. The coefficients were 1, negative 2, 4, and negative 9. Bring down the 1. 2 times 1 is 2. Total the column. Negative 2 plus 2 is 0. 2 times 0 is 0, and total the column, that's 4. 2 times 4 is 8. Total the column, negative 1. This tells us that f of 2 equals negative 1. By the way, in the next video, we're going to learn about the boundedness theorem. And if all of that bottom row had been positive, that would tell us there are no roots above positive 2. But that's not the case because of the negative 1. All right, let's try 3 with the same function. Bring down the 1. 3 times 1 is 3, total the column. 3 times 1 is 3, total the column. 3 times 7 is 21, total the column. The remainder is 30, so f of 3 equals 30. Because f of 2 was negative and f of 3 was positive, that means that there must be a solution between them. And again, on a graph, it would look something like this, not to scale. F of 2 was negative 1, f of 3 was 30. To get from point A to point B, you have to cross the x-axis. Therefore, by the intermediate value theorem, there must be at least one zero in that interval. Also, the boundedness theorem in the next video, notice that I divided using a positive value of c here, and that all the values in this row are positive. That means that there are no zeros to the right of positive 3. But you'll see that in the next video. Hear me now, believe me later. I'll see you next time.